it is that precise. This is a sense that we didn't know existed before we invented the compass, and birds have been using that for thousands, if not millions of years. So the point that I hope I was able to make is that our senses, and it's, oh, this is record. Is there any way I can remove that? We'll live with it. Senses give us a very, very limited access to the natural world. And to compensate, we must develop strategies that make judgments and decisions about the world. How do we do that? Well, there's a great book by an author named Daniel Kahneman, Thinking Fast and Slow. Who read that book? Good for you. All right. Now, all of you have to buy it and read it. All right. It's a book that was written in 2011. It was a big success when it was published. Thinking Fast and Slow is a book about how and why we make the choices we make. And what we discovered by reading the book is that it's not only our free will that leads to the decisions that we made, but that most of the time it is our biases that makes decisions for us. Is that a good resume of the book? All right, thank you. By the way, Daniel Kahneman in 2002 won let me get that straight, the Central Bank of Sweden Prize in Economic Sciences in memory of Alfred Nobel, which is what we call the Nobel Prize in Economics, but there's no Nobel Prize in Economics. That's the prize that Daniel Kahneman, a huge achievement, by the way, but it's not the Nobel Prize that Nobel himself invented. What Kahneman says is that to make decisions about the world, we use two distinct systems that he called System 1 and System 2. And so you can tell that Daniel Kahneman didn't win the prize because of the originality of his name and its naming system. System 1 is the fast system, and it's quick to reach conclusion. It's the type of system that would react to the bear entering the kitchen that I just talked about, fight or flight. Whereas System 2 is a slow system that needs time to analyze the situation before it makes a decision. Think of a math problem, for instance. So this morning you probably woke up, you took a shower, you had breakfast, you fed the kids, you took them to school, and then you took the train, the boat, the bus, or the car to come to work. Most of these things you did without really thinking about them. You were on autopilot, and even driving in a familiar environment is most of the time done with System 1, which is quite scary, actually. But that's how we go about our day-to-day lives. It's System 1, the automatic system that takes control and leads us to wherever we have to go. In my case, I woke up this morning at the very posh Royal York Hotel. Thank you very much for the reservation. I had to find out how to work the shower because it seems that every hotel in the world is trying to find a different way to confuse you about how to get hot and warm water in the shower. And so I took a cold shower at first, I have to admit. Then I had to find my way down to the restaurant, decide what I would have for breakfast, and then find a cab and make sure that the cab would bring me here instead of running around Toronto and, hiking the bill. I was in System 2 most of the time. But right now, I am high on System 2 because I have to make a lecture in front of people that I don't know in a foreign language for me. So you can tell that by the end of this lecture, I'll be completely exhausted because System 2 is very demanding in terms of brain power that you have to use to reach a conclusion or make a decision. So all this to illustrate that in most day-to-day situations, it's System 1 that takes over and runs our lives for us. And it's only when we need it really, really hard that System 2 kicks in. The problem with System 1 is that it is prone to many, many biases. And one of the major biases that I'll be using for my demonstration about the origin of misconceptions in science is a bias that we call what you see is all there is. It has a strange acronym, YZAT, something like that. But it's basically what you see is all there is. And in the words of Kahneman himself, this bias is jumping to conclusions on the basis of limited evidence. And now I'm going to give you an example of what I mean by the fact that we have this bias leads us into false conclusions. Diurnal motion. We all see the sun rising in the east, setting in the west, same for the moon, the stars, and the planets. We see that with our own eyes, but we don't feel the Earth rotation because of the law of inertia. We are taken along the rotation of the Earth at something like 1,400 kilometers per hour. And so for most people, it is obvious that the world revolves around the static Earth. And it's not because people are crazy, it's because what you see is all there is, all right? So we make conclusion based on the available information that we have. Now I'm going to show you the only mathematical equation in my talk, so if you're math anxious, please bear with me. Basically what I'm getting at is that the fact that we have limited census, plus what you see is all there is, leads people to misconceptions. That's how people build misconceptions when they try to understand how the world works around them. What is a misconception? Let me give you a short definition. A misconception is basically a personal explanation. So some people talk about the personal theory, personal model, but it's basically an explanation that people build for themselves, they construct for themselves, in an attempt to make sense of a natural phenomenon and explain its original mechanism in order to make it predictable and controllable. And these are the keywords. Because as animals, we're not the fastest, we're not the strongest, we don't have claws, we don't have sharp teeth. The way we survive in the world is by having a large brain and being able to make predictions and control what's going to happen to us in the world. That's how humanity survived. Now, misconceptions are generally based on simple heuristics, such as first impressions, immediate perceptions, false causality, analogies, common sense. What you see is all there is. These are all another expression to say what you see is all there is. By the way, we are actually in a federal election, and you might hear politicians telling you that the policies that they present are common sense. Just remember and just be slightly worried, because common sense is what tells us the Earth is flat, all right? Keep that in mind. Now, the main characteristic of misconceptions is that they are highly resistant to what I call traditional transmissive teaching, and they often persist long after instruction and into adulthood. And in my practice as a professor of science education, training the next generation of elementary and high school teachers, I can tell you that the students in my classroom and the teachers I work with in my research, they all have these misconceptions that I'll be talking about. So they're extremely common. And I'm going to give you two examples of misconceptions, and we'll try to figure out where they come from based on the idea that the limit of our senses and what you see as all there is at the root of these misconceptions. But now, first, a pause to drink water. First example is buoyancy. If you ask a typical classroom in elementary and high school, or your students in your physics or chemistry course, how do objects float? Most of the people will tell you that light objects float, but heavy objects sink. That's the misconception that we hear the most in most people. And why is that? Well, it is that way because it's easy to estimate the mass of an object or its volume, but it's much more difficult to evaluate its density. And we all know that density is the factor that determines buoyancy. Most of the time, people faced with a problem involving buoyancy will choose the most salient feature of an object, either its mass or its volume, to determine if it will float or not. What you see is all there is. That's a clear illustration of this bias at work. If you were to use system 2 to answer the question about does an object sink or float, you would have to resolve this very ugly equation that's actually the equilibrium equation between gravity and the push of water displaced by the object that you put in water. And this is absolutely system 2, whereas this is system 1, all right? If I take the nomenclature of Kahneman. Let's talk about another very frequent misconception, objects in free fall. Many people will believe that heavy objects fall faster than light objects. And if you know a little bit about the history of physics, this is Aristotle physics right there. Aristotle thought that material objects were made of 4 elements: earth, fire, wind, and water. And the more earth there was in an object, the more the object wanted to go back to its resting place, which is the surface of the earth. And so if an object had more earth in it, it would fall faster because it wanted more to go to the surface of the earth. people still believe that 2,200 years later. Why is that? Well, it's basically because we don't feel air resistance. Air, for most people, it's immaterial. It doesn't exist. Does the fish knows the ocean exists? No. Do people realize that they are surrounded by air? Most of the time, not, because it's immaterial for them. And so because we don't consider the cross-section of the surface feature of an object in free fall, it's only in mass. It's only its mass that is used by people to try to answer the question, which one will fall faster? If you were, again, an illustration of what you see is all there is. The equation, the mathematical equation to resolve this problem is even uglier than the one I showed before. And you would have to use system 2 very, very much to resolve this equation that tells you that at some point you will reach terminal velocity, both forces will be equal, and so the acceleration will be 0. So we have misconceptions. We know where they come from. It's basically because we have limited senses and because of what you see is all there is. What are we going to do about misconceptions? And in 2020, my colleague Patrice Potvin and myself, we did a vast survey of all the conceptual change models that were supported by at least one peer-reviewed journal paper. And we found 86 models of conceptual change. Now, if you're like me, the least I will say is that having 86 theoretical model to explain a phenomenon it means that it's not a very mature field of research. All right, there's way too many models to choose from, but there's one at the top that we don't see because of this bar right there, which is supported by twice as many research papers as the next one. All right, so we might think that this one has something to it that might be different from the others. This model that is supported by most or more research papers, it's the classical model of conceptual change. It was created and developed by Posner and his colleagues starting in 1982, but they worked on this model for several years. And in their model, Posner and his colleague tell us that there are 4 conditions that needs to be met, 4 conditions for conceptual change, which means that we have to create a condition where these 4 ideas are put in place for people to change their misconceptions towards the scientific concept. And these are dissatisfaction with existing misconception. There must be a new conception that is intelligible to replace the misconception. The new conception must appear to be plausible. So if I invoke fairies to explain free-falling object, I might not go far with adult learners. And the new conception must be fruitful as well in explaining new phenomena that were not necessarily linked to the misconception in the first place. I'm going to go back to buoyancy and free-falling object and see how we can use this model or this approach to try to change misconceptions. So in the terms of buoyancy, we have first to create dissatisfaction. And the best way to create dissatisfaction is just to realize that if light objects float and heavy objects sink, how can a supersized tanker ship that weighs hundreds of thousands of tons will float? It's quite heavy, it should sink, all right? So already we are toying with the misconception, and maybe the learner begins to realize that my idea might not work in all the situations that I would like it to work. In terms of intelligibility, we can tell that it's neither the mass nor the volume, but it's really the density that needs to be taken into account for determining if an object sink or float. It's basically Archimedes' principle, which, as you all know, states that an object partially or completely immersed in water gets wet. You're supposed to laugh. Yeah. It was supposed to be a joke. In terms of plausibility, yes, a large ship will float, but that's because its hull is mostly empty. And so its overall density is lower than water, and that's why it floats. And you can give many examples of other situations where buoyancy is at work. I think of hot air balloon or over water, where we can pile several different liquids on top of the other. I like the example of the submarine, because sometimes it's float, sometimes it sinks. So it's interesting to study what changed in the submarine so that its condition changes as well. What I do in my classroom is give a piece of modeling clay to my students, and I ask them to make it float. Now, obviously, it doesn't float when it's in the form of a ball, but once you build a canoe with it, it floats. What has changed? It's the same mass as before. The only difference is that by stretching it, they've augmented its volume, and so now the density is lower than water, and it floats. It's beginning to inform my students that there might be something more than their previous misconception at work. In terms of objects in free fall, the dissatisfaction might come from a discrepant event or a discrepant demonstration, a demonstration that violates the idea that people have. And I'm going to reproduce such a demonstration that I do in my classroom. So what I have here is a tennis ball and a feather. My wife works in the zoo, so that's why I have these beautiful colored feathers that comes from some tropical birds that I can't tell. You all know what's going to happen, but let me make the demonstration nonetheless, all right? So if I drop the two objects at the same time from the same height, the ball reach the ground first. Now, you all know that because of friction, all right? But for someone whose idea of friction is not necessarily present, they might just see this demonstration as a proof of their misconception, all right? The object, which is lighter, fell to the ground slower. Is there a way that we can remove air? No. Is there a way that we can equalize the effect of air on both objects? Yes. And the way I do that is by putting those two objects in a yogurt container, which has exactly the same size. Both containers have exactly the same size. They have exactly the same surface features, all right? This one is still heavier. Can you confirm that this one is heavier? Yes. Thank you very much. This is a participatory conference. All right, so what's going to happen when I drop both at the same time from the same height? Look for yourself. I just want to make sure that I do that correctly. Oh, please. You really don't have to keep that for the end. So did you see that both touched the ground at the same time? More or less. I mean, they were not exactly at the same height. I might have not dropped them exactly at the same time, but all things kept equal, they reach the ground at the same time. We eliminate the effect of air resistance, and we saw that the mass does not have an effect on the acceleration of an object. In terms of intelligibility, of course, we talk about the absence of hair, inertial and gravitational mass that are being the same to a very, very high degree of precision. Objects in free fall follow the same rate in a gravitational field, and you can show, in terms of plausibility, experiments that were done on the moon. The Apollo 15 feather hammer experiment, look it up on the web, it's beautiful. So they basically drop a hammer and a feather on the moon, and they both drop at the same time, very slowly, because of course gravity on the moon is a sixth of the gravity here on Earth. And another thing that I urge you to Google is Brian Cox, because Brian Cox visits the world's biggest vacuum. So basically, Brian Cox went to this huge vacuum chamber that NASA uses to test its satellite, because before they are flown into space, they removed the air completely. They dropped bowling ball and a bunch of feathers, and they fall exactly at the same rate to the ground. It's really, really amazing. In terms of fruitfulness, what I like to do with my students is study Galileo's inclined plane. This is not the plane that I use in my classroom. Unfortunately, I couldn't find a picture of the inclined plane that I use. But basically what you do is roll balls of different mass, but same volume down the ramp. And the gates that have little bells on them, they ring every time the bell passes through the gates. And what you have to do is put the gates at the right distance so that once the bell begins to roll, the bells will ring at equal intervals, all right? And once you've done that for one ball, it's the same for all balls. Whether it's a heavy, very dense ball or a hollow ball that's very light, they will all fall at the same rate, which is another demonstration that gravitational acceleration is independent from mass. So we have these clever ways of trying to convince people that the misconception does not help, that these misconceptions do not help them explain how the world works. We've been doing that for more than 50 years. Does that work? Well, I'm afraid that no. Even with the classical model of conceptual change, we find, and I mentioned that at the beginning of my talk, misconceptions often persist long after a thorough education. All right? It seems that conceptual change models don't really work, so far as we can tell. And the question that we began to ask in the last 20 years is, what if misconceptions never change? What if they never go away? What if they stay with us for the rest of our lives? And to answer that question, we have to ask, what happens in the brains of people when confronted with misconceptions? And we've done that following two research leads that I will discuss in the coming slide. The first way to respond to this question is by using chronology tasks, which means that we calculate the response time between a stimulus that is shown to a participant and the time it takes for him or her to provide a response. The stimulus is often a question where you have to choose between the scientific concept and the misconception. And the response time is usually measured in hundreds of milliseconds, all right? The type of stimulus that we will use look like this. So one misconception, a common misconception is that one wire is sufficient to light a bulb, right? And those two images, one is a scientific representation, the other one is a non-scientific representation. And we ask people to choose which one represents the scientific concept as fast as possible, all right? This one, it's a work that I've done with Patrice Potvin last year, where we were testing the misconception heavy objects fall to the ground faster. And we would show this image to people and they would have to decide which of the objects would fall to the ground faster. Like, for instance, a metal ball and a feather in Earth's atmosphere, and a metal ball on the moon where there is no atmosphere. And again, we will be measuring the time it takes for people to give the right answer. We discard the wrong answer because we won't need them. Sorry. And the results we get, again, this is another example, heavier objects think more. It's another misconception that is very common, like I said. The more counterintuitive the stimuli is, the more time it takes for people to reach the right answer. And so it's as if when people are confronted to a misconception that's bugging them, they take more time before they answer. They have to exert more brain power or take more time to answer the question. Another line of research that I love is putting people in fMRI machines with a screen in front of them, and we show them stimuli, the same kind of questions that I showed you for the chronology task. And we look at what's happening in their brain while they have to choose between a misconception and a scientific concept, basically. And what we find is that both in novices and experts, and that is true for high school students and chemistry professors, physics professors, name it. In all these people, the recall region of the brain associated with misconception lights up in each and every one of these people. But in the expert's brain, there is an additional zone that lights up, which is linked to inhibition, blocking mechanism. And so it seems like the expert is still carrying a misconception, but he or she has learned to block his reaction to go to the misconception and instead is taking more time to go to the scientific concept. All right? So it seems that instead of trying to change misconceptions, we might be better off trying to inhibit misconception. Because again, research shows that novice and experts have misconceptions. In the face of misconception, people tend to take more time to reach the right answer, and there's a region in the brain of experts that lights up to block the way to the misconception, all right? So the idea of blocking misconception is really an illustration of what happens in terms of the System 1 and System 2 that I was talking at the beginning of my talk. Novices who go directly to the misconception, they use System 1, all right? Gut feeling, that's the answer, I'm done. Experts, they have learned to use System 2 instead of the easy reaction of System 1, and they take more time and exert more brain effort to reach the scientific conclusion. And so again, in terms of what to do with misconceptions, it seems that they don't disappear. It seems that they stay part of our cognitive network maybe forever. And it seems also that traditional transmissive teaching and conceptual change models may have limited impact on misconceptions. Because again, we have been teaching people using this conceptual change model for years, and the misconceptions are still there, right? So instead of conceptual change, we should maybe promote what happened. Where's my friend? Is he gone? All right. Does that mean that the talk is over? Thank you very much. Oh, no problem. Where was I? Yeah, so traditional teaching, conceptual change may have limited impact on misconception. What we should be trying instead of thriving to is, instead of conceptual change, we should try to reach conceptual prevalence. And what I mean by that is that we should make sure that the right scientific answer prevails over the misconception. And that changes the way we ought to teach, right? More on that later. So students need to be warned that they have misconceptions. They need to be made aware of what these misconceptions are very explicitly. And they have to have ways to go around the misconceptions toward the scientific concept. If I may use an image to convey the idea, misconceptions are like a well-trodden path in a dense forest, all right? This path has been walked over so many times that the ground is solid as concrete and nobody will ever grow back, all right? This trail is there to stay. So what we should do when we create a new pathway for the right answer is to warn students about the trail that leads to the misconceptions and somehow propose ways to block this trail. Not by making it disappear, because it won't disappear, but by convincing our student that this is not the way to go. And they need to think harder and take their time to go towards the right answer. How do we do that? What's the secret sauce? I'm going to present you two ways that we can do that. And you'll see if you can apply them to your own teaching or your own education. The first one that I like a lot is refutation text. Who has ever been in contact with refutation text? Right. Because I was a bit worried that you would all be experts in refutation text. And I would just skip the slides. So a refutation text, this is a very short one. I mean, you can have a whole section of a book that is a refutation text, all right? But it's always following the same structure. First, the misconception is spelled out explicitly, all right? And then there is a refutation cue, which basically said, what you just read is not true. And this is followed by the third part of the refutation text, which is basically the scientific explanation, but based on some of the elements of the misconception, so that people can really make the difference between the two, all right? I'm interested in astronomy teaching, obviously, because I'm an astronomer, and John presented me as such earlier. And so I'm very much interested in the application of refutation text to teach astronomical concepts. And there is one research that was done, there's not that many, by the way, in terms of refutation text in astronomy. I found this one, which is a paper by Broughton, Sinatra, and Reynolds in 2010, where they basically compared a refutation text about the season with an expository text about the season. An expository text is basically what you find in a textbook, all right? It's basically presenting the facts. What they did was ask an undergraduate student to answer a concept inventory about the seasons before, after reading either the refutation text or the expository text, and I think 2 months later, as a delayed post-test. And what they found is that The refutation text group had fewer misconceptions at post-test, but drifted back to misconceptions at delayed post-test. So right after reading the refutation text, people were more aware of the presence of misconceptions in their thinking, but it went away quite rapidly. Now, there are two main problems with this research that has prompted me and my colleagues to do another one that I'll be presenting in 2 slides. The first problem is the use of illustrations in astronomy. You've noticed that the refutation text and the expository text, which was on another page, they both use this illustration to talk about the season. From research, that these illustrations are often at the source of the misconceptions that we're trying to change or evolve or warn against. These images have many problems. They are two-dimensional, they are not to scale, but we are never told that they are not to scale. They are what I call static or pseudo-dynamic, like there are 4 Earths around the sun. I mean, for a 7 or 8-year-old student in a classroom, that might be extremely confusing to see 4 Earths around the sun. They are also implicitly in perspective, but we are never told again. And so for novices, they are extremely difficult to interpret. And because of these illustrations that you find in every textbook in the world to describe the mechanism of seasons, you have one very important common misconception about the mechanism of the origin of the season is the distance misconception. That states basically that because the orbit of the Earth is so elongated, such a flattened ellipse, the distance between the Earth and the Sun changes dramatically over the year. And so when we get closer to the Sun, it's summer. When we get farther away, it's winter. That's how people explain the seasons most of the time. And that's the misconception that Broughton and Sinatra and colleagues tried to work in their misconception, in their refutation text. But there's another misconception that is almost as present as this one. And it is what I call the distance plus tilt. This, by the way, is an illustration that I found in the Conversation newspaper that you all know because you are, academia and the Conversation. I thought they might have done better than that, but, they probably don't know about misconceptions in astronomy. The idea of this misconception, and this again is an illustration that you find in many textbooks, you find them on Wikipedia as well. You show the Earth and the Sun very close to one another with the tilt of the Earth, which is clearly well represented. The problem is that this hemisphere is clearly closer to the Sun than this hemisphere. And so because of that, people think that the inclination of the axis of rotation is responsible for the season, which it is, but not because of the height of the Sun at noon and other angle-related phenomena, but because this hemisphere is closer to the Sun and the other hemisphere is farther away. And so what my colleagues and I decided to do was to try to work on both misconception with a refutation video instead of a refutation text. Why a video? Because in the video we have dynamic images, and I'll show you a small excerpt from this video. You can try to be more to scale than usually is shown in a textbook illustration, and you can change perspective. You can travel around, you can zoom out, you can zoom in. This was created with a 3D planetarium visualization software at the Montreal Planetarium, where I kept, contacts. And so trialing this next week. So I cannot tell you if it works or not. It's brand new, but hopefully when I come back next year, because you'll re-invite me, I'll be able to let you know how it went. But we have confidence that comparing this to a simple refutation text will lead to much better or much more awareness of the misconception at work when we talk about season. It is 6 minutes long, so I won't show you all to you. The other approach, and it'll be the last that I discuss in my presentation, is learning science by doing science. And I think this will resonate with many of you that I spoke to this morning. I had this huge schedule that Aaron prepared for me, where I met, I think, 24 people. I'm kidding. It was loads of fun. But anyway, I had conversation with many professors who teach using problem-based learning, and this is an illustration of problem-based learning, not to teach future astronomers, because that's not what I do. What I do is teach future elementary and high school teachers who will have to teach astronomy to their kids. And so it is somehow problem-based, but I think you'll find it interesting nonetheless. So the idea of learning science by doing science, I think, is a good way of first addressing misconceptions and making science learning intentional, based on System 2 instead of System 1. What I do in my astronomy course is I propose to students to do astronomy like astronomers do. This is the same thing that you do in your labs, for instance, in chemistry or in physics. You start with a question, then you have a hypothesis that is a working response that needs to be checked and validated. And then most of you do experiments. Well, I cannot do experiments in astronomy. I cannot bring a star in the lab and change its temperature to see what effect it will have on its color. The only thing I can do is observe. And this is already a difference between astronomy and the other sciences. Maybe not biology, but you know what I mean. Once I have my observations, I need to analyze them and I need to synthesize them, because there are so many observations that I have that I cannot wrap my head around them. So I have to extract from that whatever is regularities, patterns, correlations in the data. And once I've done that, I create a model. Now, you all create models in your lab, all right? But you certainly do, all right? Because he's the one who said yes. Thank you very much for your participation. When we talk about astronomy, the model has a dual purpose. The model first must explain what we've just observed. It has to reproduce the observations that we've just made, all right? But it also has to create new ideas, create new phenomena to observe that can be then made into application or prediction, communicate to the wider community, and that leads to new questions. So keep that in mind, and let's see what we can do in terms of teaching the phases of the moon. So what I did with elementary school students, high school students, pre-service elementary and high school teachers, in-service elementary and high school teachers, is launch them into a month-long observation of the phases of the moon, based on this observing log that you see there. Of course, it is very much simpler for elementary school kids. It goes into more details for adults, but the idea here is that they collect their own data for a month, for 28, 29 days. Of course, there's a good reason why astronomy was not invented in Canada. It's because most of the time it's cloudy, all right? So fortunately, we have stellarium that we can use for them to complete their observation log. And once that's done, I give them a series of questions. Those questions force them to go back to their observations, go back to the data, and find the answer, which represent basically those correlations, those patterns that are hidden in the data. And once they've done that, the next step is to create a model. And these are pictures that I took of an in-service teachers training program that I've developed and given several times, where basically, and this was 1 month after we met the first time, where they began their observations, and they've been observing for 1 month. And now you can see that they use styrofoam balls, flashlights. The top image is interesting. We use hula hoops, the one that you use to whatever you do. We stick a styrofoam ball on the hula hoop, and it becomes the orbit of the moon around the Earth. And you can time it by about 5 to 10 degrees to demonstrate that there's no eclipses every moon and every full moon, simply because the orbit of the moon is inclined with respect to the ecliptic. So we have loads of fun with that. And once they have a working model that represents what they've just observed, we can use the model to ask new questions. And one of the questions that I love to ask my students is, now that you have a better idea of how the phases of the moon work, do you think that we could see phases of the Earth from the moon? And, you know, they try to answer and say, go back to your model, use your model to try to answer that question, all right? And yes, the interesting thing is that, yes, indeed, and I'm glad that the moon is just below the bar right there. Yes, indeed, we can see phases of the Earth from the moon. What's very interesting is, what was the phase of the moon when this picture was taken? We know when this picture was taken. It was taken in December 1972. And so you can go back to Stellarium and look at the phase of the moon at the time of the photograph. And what's really funny is that if you put the moon and the Earth together, you get a circle. The phase of the moon and the phase of the Earth are always a complement of one another. When it's full moon, it's new Earth. When it's new moon, it's full Earth. Once the students have discovered that, they get it. They get it because they have a working model that they've developed, you know, by touching it, manually, by working with it. But that created a mental model of the lunar phases that they can call upon when they have to answer questions about lunar phases. And we don't have to remember all sorts of data that they have gathered. They have one working model. So their working memory is less overloaded than if they had to remember everything about the phases of the moon to try to answer a question about lunar phases. So that works. For the seasons, I did basically the same thing. The only difference is that it's very difficult in a school year to gather all the information you need about, you know, the seasons because it takes 1 year basically. So what I did with my undergraduate students in my astronomy course is give them the ephemeris of the sun on a spreadsheet, Excel spreadsheet for Montreal, and for a small city located in southern Chile called Coyhaique, which is exactly at the same longitude and latitude as Montreal, but in the southern hemisphere. So in terms of seasons, Montreal and Coyhaique are a mirror image of one another, right? This is everything I told you this morning. And so again, I have a series of questions that you have to answer by analyzing the data that is present in the spreadsheet. And I encourage them to draw graphs, plots of these different data. And this is what it looks like. So on the two graphs on the top are the length of day for Montreal on the left and Coyhaique on the right. And you can tell that it's, again, a mirror image of one another. When the length of day is maximum in Montreal, it's minimum in Coyhaique and vice versa. Same thing for the bottom part of the graph where you have the height of the sun at noon. So in June, when the sun reaches highest altitude for the year, it is the lowest in Chile, all right? Another thing that they have to draw is the apparent motion of the sun on days of solstices and equinoxes for Montreal and Coyhaique. And again, you can tell that the trajectory of the sun in June in Montreal is very much longer and higher, and the length of day is much longer than in Coyhaique at the same time. So this already convinced my students that there was something about the fact that, you know, both hemispheres have different seasons. And it was clearly not related to the distance between the Earth and the sun. It was really clearly for them related to the height of the sun at noon between the seasons. Now, to nail that idea even further, we've created the model, very simple model of the Earth, inclined at 23.5 degrees with two pins, one for Montreal, one for Coyhaique. For the sun, I would use a small flashlight with a ping pong ball glued to the lens, which is a nice diffuser. And so each student would work in pair with the flashlight on the Earth, basically. And once they discovered that the orientation of the axis of rotation of the Earth is always the same as the Earth revolves around the sun, they get it. They get it because they can tell that in one situation, the pin representing Montreal is almost overhead with the sun, all right? The sun is almost at the zenith. It's not quite, but it's almost. And on the other side, 6 months later, Montreal is still there, all right? But it's tilted away from the sun. And because of that, the sun is still on the horizon. Again, it works. It's interesting to look at seasons on other planets once the students have integrated this model in their mind. The case of Uranus is very interesting because Uranus is almost lying on its side as it revolves around the sun, but again, its axis is always pointing in the same direction. So at one point, the North Pole is pointing directly towards the sun, so it becomes the warmest, I wouldn't say hottest because it's Uranus at whatever billion kilometers from the sun, but it becomes the warmest place on the planet. And 42 years later, I think, is that, yeah, something like a half of it's the South Pole that points towards the sun and becomes the warmest place. So again, based on this model, you can find other examples of seasons in the solar system. The case of Mars, of course, is very famous and things like that. So again, it works. I want to finish with a take-home message, and Judith, this image is for you. Because when we were exchanging emails, you wrote at some point that you were looking forward to my talk because of our beautiful astronomical image that astronomers show. And I'm really sorry I don't have that beautiful astronomers. So I thought that the Pillars of Creation by the James Webb Telescope was a fitting way to thank you for your invitation. So what is the take-home message? And this will be my last slide. Misconceptions arise because of our limited senses, and what you see is all there is. Misconceptions block learning, they persist even after instruction based on conceptual change models. So we basically need to approach this differently. And the way we suggest to approach this differently is students must be made aware of their own misconceptions and learn to resist their misconception, resist system one, and use system two, which is the basis of the prevalence model for conceptual learning. And the last and not the least, learning science by doing science is a good way of addressing misconceptions and making science learning intentional and based on system two. And with that, I thank you very much.
On the Zoom chat. So if there are questions in the Zoom, please put them in the chat. But for now, for folks in the room, I especially encourage questions from students. Yeah, go ahead.
You have to speak loud because I told you I'm going deaf. So
here in your discussion about misconceptions, and you had a picture on the projector on the screen of a trail, one leading to a wrong answer, one leading to a right answer. Could you relate that in a sense to like motor learning and for example, repetitive action over and over and over again, like rehab or something?
Well, misconceptions sometimes arrive. Those misconception has something to do with repeating the same thing over and over again. Was that?
In a sense, yeah.
Okay.
And then the other half was that also if you're doing something over and over again, you're like training your, as you mentioned earlier, you're training your body to think differently.
Yeah. To answer the first part of your question, when you see a small child, a toddler, playing with wooden blocks, dropping them on the ground repeatedly for hours, it can be pretty annoying. This child is learning gravitational free fall. All right. And the more he will or she will repeat the gesture, the more this idea that heavy objects fall faster will be ingrained in his brain path, right? And that's the analogy that I was making with the path well trodden where nobody will go again. So what you have to do is convince that person once she or he grew up to be wary of that path and to use another one. And this can be done differently. Well, I showed you two ways that it can be done. And it seems to be working fine. The idea is that people should be convinced first, that they have misconceptions. Second, that these conceptions won't go away. And so they have to be aware of not going towards the misconception, but use the scientific concepts that they have learned at school.
I'm a chemist. I had a student just come into my office this morning saying how much he enjoyed doing the labs because it really reinforced what he'd been learning in the chemistry class. So as a corollary to your talk, and you learn by doing, and you need the physical experience to help you cement these ideas, what is your take then on online classes versus having labs and learning from doing? Because online, you're not going to do any of this except just passively learn.
And that's why online learning is not that good. And there's only so much that you can learn by reading or by watching someone talking to you instead of doing it for yourself. A lot of you are using problem-based learning in their classroom, and I think it's a genius approach because again, people learn science by doing science, either in chemistry or physics or any other field. So I think we were kind of forced to go online because of the pandemic, and some people thought that it would be a good way to continue their teaching, but it might work in some areas, like for instance, in philosophy, if all you do is discuss, that can be done online. But physics, chemistry, astronomy, no. I think you need the experience with the real data. You need to be able to, get your hands dirty to learn.
In classic education, like in high school and elementary, I think there's a big emphasis on understanding, just knowing a fact or being able to produce an output once given in prompt. And that can be because of like lack of resources or time management. But would you think that possibly in the future, maybe there could be a role for artificial intelligence to somehow fill that gap in resources and time management to give that?
I'm not sure I agree with your conclusion there. I think that the way sciences are taught in high school has more to do with the size of the curriculum and the fact that the teaching is evaluated with multiple choice questions. So what is valued in high school is retaining information, all right? In Quebec, I don't know the situation in Ontario, but in Quebec, in the fourth year of high school, every student has to take a science test. And it is basically a 50-question multiple choice test. So what it measures is retention of information. So the teachers in their biology and physics and chemistry class who know that they will have to prepare their students for this test, what do? They work on retaining information. Because of the curriculum, there are so many things to be covered that a science teacher in high school will probably spend 1 hour teaching the seasons, 1 hour teaching the phases of the moon, and that's it. So what kind of learning is happening in 1 hour when we know that the misconceptions are so deeply entrenched and they're so hard to prevent students from going to? It takes more time. So what I'm advocating for is having less in the curriculum, but spend more time on it and doing it by problem solving. And I think that would revolutionize completely the way we teach science in high school. It's already how we teach science in elementary school in Quebec, because the curriculum is very open. Teachers can basically do what they want with it. And what we train teachers to do is basically to make sure that their students are doing science the way science is done. And it seems to be working, but once the students reach high school, they hit a wall. And it's unfortunate.
Sorry, just a quick follow-up to that.
It's hard to decide. I'm not taking sides. Go ahead.
So you said there's a lot, and you suggest that we reduce the curriculum down, but
Which is impossible to do because curriculums are made by committees. And everybody wants his piece in the curriculum.
So what would you suggest as an alternative to like not block a path that a student might want to take? Because, let's say they wanted to pursue science, but they did, and they felt they wanted to go more into the arts, but they couldn't really have that balance. If that makes sense.
I don't know how it relates to blocking the path to
Like, because
misconceptions, but.
There's less in the curriculum, so there's less paths to take.
Oh, no, I mean, you can have all the choices you want, but I mean, in terms of content, for the science curriculum, there is less. In the arts content, there is less. So you can go more deeply into learning the different
I see.
facts that are included. Maybe it's my poor English that left you hanging, but no, that's what I meant. I'm not meaning that we reduce the choices that the students have. I meant that we reduce the size and the content of the curriculum of each of the topics that they have to learn. All right?
Fascinating. Look, I just have a.
You always say that.
I'll be reading from misconceptions are here to stay. That's what you're saying. We need to kind of find ways to mitigate. Can you comment historically if the percentage or amount of misconception has decreased over, say, the last 50 or 100 years or 2,000 and 200 years? Can you comment on that? Do we live in an era of information?
I don't think that it was ever measured, so I would have to go with my gut instinct. I think that we have more. Because of this information overload that we all live in through social media and the internet and things like that. Because people are aware of more phenomena than before. And each of these phenomena is probably linked to a misconceptions that people have. Because again, our senses are limited, we jump to conclusions and we make false judgments.
Because we have more input, we have more misconceptions. That's what you're saying.
I mean, in the Middle Ages, people didn't know how to read. They probably didn't have very much information about, astronomy, chemistry, and things like that. So the number of misconceptions were probably limited because of that. Nowadays, you can read about all types of subject on the internet, and so you can form as many misconceptions as you want. And I'm not talking about misinformation. That's another beast. That's linked to something else. I'm talking about people trying to understand phenomena in science, and because of these limits that I just talked about, they form bad ideas. No, I want to say bad ideas, but ideas that are not congruent with the scientific concepts.
This actually leads beautifully to my question. It seems to me that we're kind of devolving away from misconceptions into literal falsehoods being promoted as knowledge.
Absolutely. Like the earth is flat. Jeez. Sorry.
Yeah. And to me, that's, I'm not an astronomer, but to me, that's a less dangerous one to me than a lot of the other misconceptions that are also being pushed to a point where we feel we have different realities of information and different realities. And so that my misconception for one concept is also a misconception for another, but for completely different reasons.
Yeah.
How do we fight when neither of us believe the source information?
I don't know. But you raise an interesting point. When I made a joke about the fact that people believe that the earth is flat. My father was a land surveyor. And in his day-to-day job, for him, the earth was flat. Not because he thought that the earth was not a sphere, but because in his work for making calculation and measuring angles, the flat earth was exactly what he needed. So we might argue that misconceptions is maybe a right idea in the wrong context. Because again, and I remember at some point I was working with him during summertime, and we had this job to do for Hydro-Québec to measure a transmission line that went from La Grande in the James Bay region down to, I think, 600 or 700 kilometers south in a straight line. And I remember that my father told me that for this calculation, he had to take in consideration the fact that the earth was curved because the context had changed. So There's a difference between people who have misconceptions, but they are ready to learn. And for these people, I think the approaches that I proposed and other ways work perfectly. But then there are people who have ideas who don't want to change. The flat earthers, for instance, if I may bring back this example, they don't want to change. They're convinced. We are in the realm of faith, not in the realm of science. And for these guys, I think there's nothing we can do, unfortunately. Yeah.
So the question is, in your presentation, you spoke about inhibiting misconceptions rather than ignoring the misconception. Have you explored how this relates to knowledge retention regarding the misconceptions, I guess, over the long term?
Knowledge retention, it's basically memory. If you use a concept, oftentimes it will stay with you. If you use it only once to answer a multiple choice question and you forget about it because you don't use it anymore, it won't stay. That's why I think that a curriculum based on retention is not working, because students, when they don't use the concepts that they have learned, they will just lose them. Whereas if they have really worked hard to develop an idea, a concept like the phases of the moon, the seasons, it stays with them because, you know, they've invested a lot of energy and time and brain power in it. So I don't know if that answers the question, but.
Yeah, I think for reasons of time, we have to cut it off there, but thanks everyone for your questions, and hand it over to Claudia.
Okay, so Pierre, thank you very much for a wonderful lecture, for using your system 2 at max.
Oh, gee, I'm sorry.
I promise you for at least the next half an hour, 45 minutes, we'll make you system 3, which is enjoyment and conversation. So no more logical thinking, I hope. And please, there are a couple of students in the room. Do not talk to people that look above 30. Just try to only talk to young people, or at least for the first time of it. They were pretty shy to ask questions, but you know.
Well, we'll have dinner together and we'll have a long conversation about their future, so.
I won't keep you long. I just want to give you a small gift, and thank you for coming, and
Thank you very much.
have refreshments outside. Please go socialize, enjoy, and talk about conception.